This video looks at unbiased prediction. Now, the previous videos have shown how you can form compact forms for predictions using state space, GRIMA or step response models. However, we gave very little attention to the accuracy of these predictions in the presence of, and this is key, disturbances or parameter uncertainty. It transpires that when you're doing predictive control, the most important time to be accurate is in the steady state. That's not to say, by the way, that transient errors aren't important too. If I'm in the right steady state, the right place already, what I don't want is the prediction model telling me that I'm going to move from that place, because clearly that cannot be true, and so there's a problem. This video is going to look at how we can ensure that the predictions are unbiased in the steady state, which means that once you're in the steady state, the predictions predict that you stay in that steady state. What causes our predictions to go wrong is clearly uncertainty. Now, we're going to deal mainly here with disturbances, but implicitly we're also dealing with parameter uncertainty. So assume you have a system, there it is G, which has an input U, and then assume that this system is subject to some form of output disturbance D. Then the overall output is going to be given by an equation a bit like this: y equals GU plus D. And the key thing is it's not given just by GU, there's a plus D term there. And that's what we're going to look at. How does our modelling and our prediction, how does it get affected by this scenario? Let's have a look then what happens when you're in the steady state. You can see in this particular picture we've set the output, it's already got to a steady state, and the input is already at a steady state. So if I assume that the input, that's U down here, stays at the same steady state, there it is, and I was to form the output predictions assuming the disturbance and the input do not change, then what you'd be saying is, well, clearly a sensible prediction would be that the output stays the same. However, if you have an error in your modelling, so the gain of your model does not match the gain of the real system, then what your predictions might do is something like this. And here you'll notice you have an offset. So your predictions will not match what should be happening. Now, when this happens, we talk about the predictions being biased. Okay, so the steady state of the predictions does not match the steady state they should give. And if you try to use biased predictions in a predictive control law, then you'll get problems. So what we want to do is investigate how can we ensure that we get this prediction set here when we're in the steady state. We're going to look at the earlier prediction equations given in the earlier videos and establish whether these are biased or not. So do they give the correct steady state or don't they? Now, these tests must implicitly allow for both parameter uncertainty and disturbances, because both of those will be present in practice. The assumption will be that the past state is constant, i.e. we're assuming we're already in steady state, and we're saying if we're already in steady state, does our model give us the correct future predictions? Okay, let's start with a state space model. What we're going to do is we're going to use our one step ahead prediction model, which is a standard state space model, and ask ourselves, does this work correctly? Now, if you're already in steady state, the predictions should be time invariant. Now you'll see what I mean. So here we go. We've got our standard state space model, which I've circled here, yk equals cxk plus dk the disturbance, xk plus 1 equals axk plus bu. Now we're going to assume these are the model parameters, not the actual process, which is unknown. If I go one sample forward in time, then the output will be this: yk plus 1 equals c xk plus 1 plus dk plus 1, and we're going to assume the disturbance is time invariant, so it's constant. Now let's see what happens here. If I'm in steady state and I expect to stay in steady state, then I should get that yk plus 1 equals yk. And what that tells me, looking at these two equations here, perhaps if I change the colour, these two equations here, is it tells me that xk plus 1 must be equal to xk, or equivalently x is at a value such that x equals ax plus bu. So we don't expect the state to change in our predictions if we're already in steady state. What next then? Well, if we look at our model output is given as this: cxm plus dm, where dm is an estimate of the disturbance, whereas our plant output is given by something like this: yp equals cp xp plus dp. So you notice the state is slightly different and the c is slightly different, and obviously a different disturbance. Now you could say that this is the real or the actual disturbance, but what we're interested in is dm, because dm is what we're going to use in order to get our predictions correct. Now if I solve these equations, you can see fairly clearly that dm is given as yp minus cxm, so I can get an estimate of the disturbance required to give me the correct steady state. Now, getting the correct disturbance estimate is critical to ensuring we get unbiased predictions, as you will see. Now you might like to prove that this works. Here's a prediction for all the future values of y based on a state space model, and this is covered in one of the earlier videos. What you might like to do is prove that if you assume that x is at a value such that x equals ax plus bu, and in addition you use as the disturbance estimate d, yp, that's the actual process output, minus cxk, where x is the model state. So you notice here we've linked up, there's a process output but a model state. So if you define d like that, then what you might like to prove is that these predictions here actually ensure that y future equals yp, 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 and so on down. And we'll leave that to you, and you should find it's relatively easy to do. What we're showing then, or what we're trying to lead you towards, is the fact that a disturbance estimate is a good tool for ensuring that we get unbiased predictions. Now if you're in steady state, you can write two expressions. You can get the process output is given by the process disturbance plus the process gain times the input. Now that, if I put there, that's process. In fact, we don't know the process, so we have to use a model. So our predictions are based upon the model, which gives you ym equals dm plus gm of 0 times u. And you'll notice we've been careful here to write that the disturbance estimate dm is not necessarily the same as the actual disturbance dp, because this dm not only takes account of the disturbance, it also takes account of the fact that there could be some uncertainty in the parameters. Now, the output predictions will be unbiased if we can ensure that yp equals ym. In other words, dp plus gp0u equals dm plus gm0u. That's what we're going to need to do. So how can we find a good value for this disturbance estimate? Well, we're going to do a little cheat here. What we're going to do is we're going to say, if I put it here, gp0u plus dp is clearly equal to the actual output. And that we're going to treat as known because you can measure it. So we know half the equation, we know what yp of k is. So if we substitute that in, then what we get is this: yp of k equals dm plus gm of 0, or in other words, and this is the key thing, your disturbance estimate is given as the current measurement of the output, we're assuming at steady state for now, minus gm of 0 times u. Now clearly gm of 0 is known because it's a model, and u is known because you choose the input, so you can get a disturbance estimate. So if you're at steady state, you can get a good estimate for an appropriate value of dm to ensure your predictions are unbiased. Okay, in practice, we're going to find the model output as based just on the system model and without a disturbance. So I'm going to define ym of k as just coming out of the model. And then I'm going to add a disturbance onto it. So what you can do is you can do this instead. You can write that a good estimate for the disturbance is the process output minus the model output. So in other words, you have the process which you can measure and the model which you can produce using your model parameters, and the difference between those two values essentially reduces to the estimate of your disturbance. Now in practice the system is rarely in steady state, so we need this improved estimate of disturbance to ensure the predictions are unbiased even when we're not in steady state. And so this simple formula is the most convenient and appropriate because it doesn't rely on us being in steady state. In other words, we can just write down this as our estimate of the disturbance. And you'll notice this works in steady state, but we can also use it when we're not in steady state. And the nice thing is it also captures parameter uncertainty as well as real disturbances. So this is the tool we're going to use, this equation here. You'll find it's very common in the literature to write the disturbance estimate in this form, and clearly it changes every sample because it's based on the current measurement of the process and the current output of the model. Now here's a little picture to demonstrate what's actually going on here. You'll see in this red sort of ellipse we've represented the real process. Now the real process has got some sort of disturbances which you don't know, but what you can do is you can measure the output of the real process. What you can do is you can construct a model, that's GM, you can put the same input to the model as you're putting into the process, and you can get a model output YM, and then you can use a summing junction to find the difference between these two, and that gives you the disturbance estimate. And what you'll notice here is something interesting. The model GM is used in two different ways. We use it to form the nominal predictions, which is YM future, and we also use it to estimate the bias term DM. So those are the two things that we need. Now in summary then of unbiased predictions, and what we're giving here is the method which is most common in the literature, and reminding you that this allows for both the real disturbance, which is unknown, and in fact errors in the parameters. So what you do is you say your future predictions for the real process are given by your future predictions for the model plus your disturbance estimate, and your disturbance estimate is given by yp of k minus ym of k. So a very simple form indeed. And if you use this prediction model, it will ensure that you get correct prediction at steady state, and thus the model will not cause any steady state bias in the control action.